A 99% of life on Earth is small. Why were dinosaurs so big? Their sheer scale defies modern biological possibility for land animals. But to understand their size, we must first examine their ancient world. The air they breathed was significantly different from ours today. Oxygen levels were elevated, potentially reaching 30%. This hyper-oxygenated environment fueled massive metabolic requirements. But this rich supply allowed for sustained high-energy output necessary for growth. And now that we understand the air, let's explore their internal architecture. Modern reptiles are ectothermic. Dinosaurs exhibited remarkable endothermy. They needed extremely efficient cardiovascular systems to pump blood. But their skeletons were masterpieces of weight reduction and strength. The pneumatic bones, hollowed by air sacs, saved colossal amounts of weight. This structure supported tons of mass without collapsing under gravity. Furthermore, dinosaurs evolved an upright posture, unlike sprawling ancient reptiles. This columnar limb arrangement maximized load-bearing capacity dramatically. And now that we understand structure, let's examine dietary implications. The giants needed vast quantities of low-quality vegetation daily. Digestion in these megaherbivores was a slow, massive undertaking. Stomach stones, or gastroliths, were essential for grinding tough fibers. This size conferred a huge advantage in accessing untapped food resources. For predators, immense size translated directly into overwhelming hunting power. Their sheer bulk made them nearly immune to predation once mature. This created an evolutionary arms race driving subsequent generations larger. Growth rates were astonishingly fast for animals of this scale. Fossil evidence suggests some reached maturity in decades, not centuries. Their bone histology reveals growth lines akin to extremely fast-growing modern birds. This rapid growth mitigated the risk associated with long juvenile periods. However, gigantism carried inherent logistical and energetic challenges. Moving immense bodies required incredible, sustained caloric intake. Heat dissipation became a critical engineering problem for the largest species. And their sheer volume meant they had a favorable surface area to volume ratio. The fossil record provides physical evidence for these anatomical solutions. But coordination across such a vast nervous system also posed challenges. But even simple actions, like lifting the head, required massive muscle power. Compare this to early mammal ancestors, constrained by smaller lung capacity. But dinosaur respiration involved highly efficient avian-style air sacs. But this allowed for continuous oxygen uptake, fueling their enormous bulk. On geological stability during the Mesozoic also supported this large body plan. While warmer global temperatures meant less energy expenditure for thermoregulation. Abundant plant life provided the continuous fuel source for the largest species. But each step left an indelible mark, a testament to their physical dominance. A predation pressure during juvenile phases pruned any lineage that couldn't grow fast. A reaching giant sizes became the ultimate defense mechanism for the dinosaurs. Their bones achieved maximum strength through a unique, porous internal structure. A gigantism appeared independently across different dinosaur lineages. But this suggests the environment strongly favored large body mass carriers. But the higher atmospheric pressure also aided in gas exchange efficiency. They exploited ecological niches unavailable to smaller contemporaries. But these factors coalesced during a period of relative global tranquility. A bone marrow in these giants likely supported faster blood cell production. They were the logical biological endpoint of their specific environmental parameters. Or yet, achieving this immense size meant extreme vulnerability during early life stages. These social structures likely evolved to protect these massive investments in offspring. The long lifespan afforded by size allowed for greater reproductive success. Uneven egg sizes were optimized for rapid development within the shell. This biological success story was ultimately contingent on global stability. But when conditions shifted dramatically, their immense size became a liability. Smaller animals required fewer resources to survive the resulting darkness and cold. The very adaptations that allowed gigantism sealed their ultimate fate. But their size was a perfect product of their time, a biological triumph.